Good evening. My name is John Mulcahy. I'm the acting director here at Carnegie Observatories. It's my pleasure to welcome you here tonight to this really unique and exciting event. It's so great to see so many people here. I'm guessing from looking around, a lot of you I don't recognize, which means many of you are probably here for the first time. Is that the case? Yes? Yeah, well, welcome. Yes. I'm curious how many people here actually never heard of us before this event. Some hands. Yeah, excellent. Lots of hands. Most of the hands, in fact, for those of you who can't tell. We like to refer to ourselves as Pasadena's best kept secret, and for good reason. Clearly, many of you didn't know about us. We've been here a very long time, since basically 1902, this property you're seeing at. Yeah, we're actually one of the oldest things here in Pasadena. And as you'll learn about tonight from our astronomers, pretty much all the major discoveries, I shouldn't say all, but all the very important astronomy discoveries of the last 110 years happened right here in this building here. And so you're going to hear about that from our astronomers tonight. So it really is a legacy here in Pasadena that many people don't know about. Tonight, I was going to start by, I'll introduce our astronomers first, but actually before I do that, let me thank the other partners tonight, which is the Pasadena Conservatory. Let's give them a hand. And so tonight we're going to be combining art and science, or in this case music. For many of us, myself, I don't know, some people know this, not many, I'm actually a songwriter myself, and so it's very common for astronomers and other scientists to have multiple talents and be interested in art and science. And so tonight we're going to actually combine those two. For the 100-year anniversary of our observatory here, our staff was asked what we really wanted the most. And the answer was we wanted theoretical astrophysicists. And this is a new thing for us. This is an observatory, as you hear. We usually, most of us, like myself, spend our time looking at the universe through telescopes. But we've made two recent hires, and those are our speakers tonight, Juno, Kollmeyer, and Andrew Benson. And their specialty is actually theoretical astrophysics. That is, they take the laws of physics and they work on computers, and they actually make predictions for what the universe should look like and how it works. And that's very important for observers like myself. They basically help us interpret the images that we take. And so I'm very excited that you get to hear from two of our youngest and most exciting staff members tonight. Before we do that, I also wanted to thank Steve McCurry, where is he, somewhere around here, where is he? Who helped set things up. You'll hear from Steve a little bit later. Let's give him a hand. And I wanted to thank Erica Clark, who's a consultant here, who helped us on the Carnegie side set us up. And last but not least, the Pasadena Arts Council, which is hosting the AxS Festival, of which this is a part of. So we're very excited to be participating in that. So with that, I'm going to introduce Juna Kollmeyer. Come on up. Are you going first by yourself or combined? Juna will start us when you hear a history of astronomy here in Pasadena.
Okay, thank you, John. Well, welcome everybody. It's so exciting to see you and to be at this this event, the first of, I hope, many future sort of collaborations of this nature. So tonight we're going to talk about curiosity, since that's the theme of the AxS Festival. And in particular, we're going to talk about Mount Wilson and the nature of space and how important Pasadena has been in showing us what the nature of space is and sort of the discoveries that have led to our understanding of our universe. So I'll talk about the historical part, and our story begins with these three guys. So Ben Wilson, George Hale, and Andrew Carnegie. Ben Wilson, as many of you may know, the denizens of Pasadena anyway, the second mayor of Los Angeles, and he was one of the owners of Rancho San Pascual, which is where we are now. That was eventually subdivided into Pasadena and Alhambra and San Marino and many of the places we call home. And of course, this is the namesake of the Mount Wilson Observatory and Mount Wilson itself. And so many of you, how many people have actually been on the Mount Wilson Trail? Okay, more people than know about Carnegie. Okay, good. So, next is Andrew Carnegie. So unfortunately, you can't see the quote because of these trees. But what Andrew Carnegie really sought to do, or at least he believed that he wanted to do real and permanent good in the world. And he believed very strongly that it was important to use the wealth that he had amassed in his maybe not so nice career as a businessman to really enrich communities and to sort of provide a legacy for the future. And so what I've done here is I've just photocopied, or not really, I took a picture of the Carnegie's first yearbook from 1902. So that was the founding of the Carnegie Institution of Washington. And you can see that he says, I, Andrew Carnegie, having retired from active business and deeming it to be my duty and one of my highest privileges to administer the wealth which has come to me as a trustee in behalf of others. And what he wanted to establish with the Carnegie Institution of Washington, and you can see there were some pretty high-level trustees. So, the President of the United States was an ex officio trustee of the original Carnegie Institution. But what he really sought to create with the Carnegie Institution was to secure, if possible, for the United States of America leadership in the domain of discovery and the utilization of new forces for the benefit of man. And that's really what he sought out to do. But Carnegie was not a scientist. He was a businessman. And so another one of Carnegie's quotes was, "Here lies one who knew how to get around him men who were cleverer than himself." And so the first thing that Carnegie did was he established 18 advisory councils. And each of these advisory councils was in a different area of discovery, in physics, in astronomy, in chemistry, in paleontology, in all of the different areas of discovery at that time. And he assembled these committees to give him reports and to give the trustees of the Carnegie Institution in 1902 reports on how this institution, this trust, could best serve the areas of science that weren't being served in the universities of the time. And remember, this is 1902, so the United States is not by any means kind of research power that it was later to become. And one of the key members of the Committee on Astronomy was George Ellery Hale. So George Ellery Hale was on this advisory committee, and one of Hale's greatest quotes was, "Make no little plans." So George Ellery Hale was to build the largest telescope in the world 3 times. He started first at the Yerkes Observatory in Chicago, and this was, at the time, it was a great facility. He was the first director there. But as many of you who've been to Chicago know, it's not so nice there in terms of the weather. It rains a lot, and that's not so good for observing. And so he actually was seeking clearer skies. And as many of you have also observed, we've got some pretty good weather here in California, in Southern California. And in particular, Mount Wilson has excellent air stability. So it was known at that time that it was an excellent site for astronomical observations. And so immediately in 1902, Hale, as part of this advisory committee, started pitching to the Carnegie Institution, to the trustees of the Carnegie Institution, that it was very important to build an observatory at Mount Wilson. And in fact, in 1904, Mount Wilson Observatory is founded. So the 60-inch telescope operated essentially as the largest telescope from 1908 to 1917. And then after the 60-inch telescope, a 100-inch telescope was built, and that was operational. That was the largest telescope until the Palomar 200-inch, which George Hale also built, was founded down on Mount Palomar in San Diego. So let me just sketch the sort of state of the scene in 1917. So 1917, that's the year that the United States enters World War I. The 100-inch telescope was safely delivered to Mount Wilson during that period. Edwin Hubble, one of Pasadena's most famous residents, was just finishing up his dissertation entitled Photographic Investigations of Faint Nebulae. And he actually moved up his dissertation defense in order to join the conflict. And in 1917, you have to remember, this is only 1 year after Einstein has published his theory of general relativity. And so this has really thrown physics and science into a sort of great kerfuffle about sort of the nature of space and the nature of time. And at this time in astronomy, it was unknown whether the Milky Way galaxy was just one of many galaxies in the universe, or if it was itself the entire universe, if the Milky Way was large or if it was small. And when I say these faint nebulae, this is what people were looking at that time. So this is actually this is a photograph of a plate from the 60-inch telescope taken in 1910 by George Ritchie. This scan was courtesy of Dan Cohn. And at this time, this is a pinwheel galaxy. We know these things as external galaxies, but at that time, it wasn't known if these were galaxies. People thought maybe these were just individual stars in some phase of their evolution where they were giving off lots of dust and lots of light. At this time, it just wasn't known. But with the construction and establishment of the 100-inch telescope, it was possible to sort of end this debate about these faint nebulae and about the size of the universe. That in fact, the Milky Way was indeed a large galaxy, but these faint nebulae were external galaxies. And this is, I call this the plate that ends the debate. So this is the photograph that Edwin Hubble had taken of the nearby Andromeda galaxy. And you can see in red, up in the upper right-hand corner, it says VAR. So this famous plate, these are using a special type of variable star. Edwin Hubble was able to determine that these galaxies, that these nebulae, were indeed external to the Milky Way, that they were indeed very, very far from the Milky Way. And in fact, at Carnegie's 100-inch telescope, Edwin Hubble was able to determine what he called the magnitude-redshift relation. And this is the relationship between galaxy distance and velocity that tells you that the universe is indeed expanding. So the expansion of the universe is one of the most fundamental discoveries that really has ever been made in physics. And this is just showing you an animation of what that expansion might look like. So each one of these things are little galaxies, and you can see that they expand apart from one another, and the galaxies themselves don't expand, but these galaxies recede away from one another, and space itself is expanding. So this is, as I said, this was near to the time that people like Albert Einstein and George Lemaitre and de Sitter were really grappling with the nature of the universe, grappling with its geometry, with the nature of sort of space. And what Einstein said in response to this discovery was, "This circumstance irritates me." So Einstein didn't really like the expansion that much. And so what he did, because he really wanted a static universe, and so what he did was he put a term in his field equations of general relativity that would make the universe static. This term actually has in later time been discovered very recently, partly due to Carnegie astronomers, to be what we now call dark energy, that is the accelerated expansion of the universe. And so even though this irritated Einstein, sometimes theorists get irritated and we just have to deal with it because the observers see what they see, and that's how the universe is. But the point is that bigger telescopes allow us to see farther, and they allow us to see things more clearly. So this is the 60-inch on the left, progressing up to the 100-inch at Mount Wilson, the 200-inch at Palomar. Subsequently, we have the 6.5-meter telescopes at Magellan in Las Campanas Observatory in the Andes, the Keck telescopes in Mauna Kea. And let me just give you sort of a visual demonstration of how this, why we want these big telescopes and how they allow us to see things clearer. So I'm just going to show some galaxies, and you're first going to see a very old Palomar image of these galaxies, and then you're going to see the Hubble Space Telescope image of the very same galaxies. And these galaxies just come into crisp view. What looks like just a haze turns into different stars, and all of the structure that you can see within these galaxies. These are very nearby galaxies where the Hubble Space Telescope is able to sort of perform images at this clarity. And you can just see all of those individual stars and star clusters resolve into very, very detailed structure. And it's exactly this type of structure that people like myself and Andrew Benson are aiming to understand. So we'll just show a few more of these. And we'd like to see further and further. And so the next telescope that we're sort of in the process of building is the Giant Magellan Telescope. And this sort of continues in the history of Pasadena building larger and larger telescopes to make fundamental discoveries about the universe. And this is just an animation of what that telescope will look like. And this telescope will have a 25-meter diameter. And in fact, many of you who came in the parking lot saw circles on the ground. And those are that's the actual size of the mirrors of this telescope. So we're really excited about what the future will bring in terms of Pasadena and Pasadena's role in discovering the cosmos, figuring out what dark matter is, what dark energy is. And now I'm going to just let Andrew Benson discuss some of the modern things that we're working on here.
Yes, I'm going to try and in the next 15 minutes tell you a little bit about what's happening at the Carnegie Observatories today. As John told you, Juna and I are both theoretical astrophysicists, so I will focus a little bit on some of the theoretical work we do trying to understand the nature of dark matter. So I'll try and explain to you what dark matter is, why we think it's out there, and why astronomy is really the only way that we're able to learn about what turns out to be the majority of our universe. So it turns out that we first learned about dark matter due to a Carnegie astronomer. In the very early 70s, Vera Rubin was interested in looking at galaxies such as this one. This is a nearby galaxy, rather like that of our own Milky Way. So it's a big disk of stars, billions of stars, all rotating around the center of that galaxy. And Rubin wanted to know how fast those stars were moving. And so what she did was to point a telescope at this galaxy many times at each of those white dots and measure how fast the stars were moving. Why did she care about how fast stars were spinning around? Well, the faster something is spinning around, the harder it is to hold it in place. And in galaxies, the thing that holds them together is gravity. So if you measure how fast a galaxy is spinning, you can actually figure out how much gravitational pull it has. And gravity comes from mass, so this is a way of weighing a galaxy, of figuring out how much material it contains. And so Rubin made these measurements and found that this galaxy was spinning around much, much faster than anybody expected. In fact, so fast that the gravitational pull of its stars would be unable to hold it together. But we know these galaxies have been there for billions of years, so clearly they must hold themselves together. And so the idea of dark matter was born. There must be some other mass in this galaxy that doesn't emit light, we can't see it, but we can measure that it's there based on its gravitational pull. And what I'm going to do is show you, first of all, some theoretical calculations of what we think dark matter looks like, if we could see it, and then spend a little bit of time really trying to convince you that we have a lot of evidence that there really is dark matter in the universe. So the first thing I want to show you is a movie, and we're going to loop this a few times. This is a computer simulation of what dark matter would look like if you had special dark matter glasses and could look out into the universe and actually see it. This is one of the great things about being a theoretical astrophysicist. We don't have to stick with the rules of the universe. We can make dark matter visible if we want, at least in our computer simulations. So what you're seeing here is a whole bunch of dark matter starting out in the very early universe, where it was quite smoothly spread around, for example, right here. But then the action of gravity likes to pull things together. So as time goes on, and you're seeing billions of years of the universe pass by in a few seconds here, gravity pulls this dark matter together to form bigger and bigger systems of dark matter, little dark matter blobs. So the brighter the colors in this image, the more dark matter there is in that region of space. And we can freeze this and just look at what happens if we rotate around one of these systems of dark matter. And this is actually what we think the dark matter around our own Milky Way galaxy would look like if we could see it. And you'll see there's not just one blob of dark matter, there are many. And potentially each one of those could form its own galaxy. So I'm just going to show you here a single snapshot of dark matter in the universe, again based on a computer simulation. And I always find these incredibly beautiful images. So what you're seeing here is the distribution of dark matter across a huge region of space. Traveling at the speed of light, 186,000 miles per second, it would take you almost 1 billion years to cross from one side of this image to the other. So this is a really huge region. And you can see that gravity has sculpted this dark matter into this beautiful, what we call cosmic web, of filaments connecting together dense regions of dark matter in which galaxies themselves would form. If I zoom in to just that single blob right in the center, you see this spectacular structure. And this, again, is the kind of dark matter system that we expect our own Milky Way galaxy would form in. And to give you an idea of the scale here, our own Milky Way galaxy is about 50,000 light years across, but it would be a tiny speck in the center of this image. This is still a really vast structure in our universe. And once again, you can see that there are thousands of other systems of dark matter all spread around nearby. But it turns out we actually have a lot more evidence than just the rotation of galaxies that convinces us that there really is dark matter in the universe. And I'm going to go through just a handful of those to really convince you that it's there. And all of these are based on astronomical measurements. Astronomy is the only way we know about dark matter. So it turns out one of the main ways, perhaps surprisingly, that we know about dark matter is from the Big Bang, the event that started our universe. That happened about 14 billion years ago, but the light from it is still around. It's been expanding and fading ever since. But if you look very, very carefully, with a satellite such as this, the Planck satellite, which was launched a few years ago, you can still detect that light from the Big Bang. What this satellite does is to look across the entire sky. It makes a map of the entire sky, but not an optical light that we look at longer wavelengths. It looks in the microwave region, because that's where this light from the Big Bang can be found. And this is what it sees. Now, this is not the Big Bang. This is our own Milky Way. Our Milky Way is very bright in microwaves, and you can see it as this band right across the middle of the image here. But that's not what they were really interested in, so they had to work very hard to remove that. And what they wanted was what was left behind after you take the Milky Way out of that image. And this really is the light from the Big Bang that you're looking at. And it's not perfectly smooth. The red parts are slightly warmer, the blue parts are slightly colder. And the reason some parts are hotter and some parts are colder is because the universe was slightly more dense in some regions than in the others. It contains slightly more dark matter in one part than in another part. There's a very, very tiny difference. The hottest regions here only differed by 0.001% in the amount of dark matter they contained compared to the coldest regions. So the universe was very, very smooth, but if we look around us today, the universe is anything but smooth. There are galaxies and stars and planets that are all very, very dense, even though most of the universe is completely empty. So how do we get from that very smooth early stage of the universe to what we see around us? The answer, once again, is gravity. But if you do the calculations, it turns out that the gravity of stars and gas, normal matter, is just not enough to get you from the Big Bang to the present-day structure that we see in 14 billion years. You have to add in a lot of extra mass, and that mass, once again, is dark matter. So another piece of evidence. And if you actually look at this map carefully and perform some calculations, we can figure out that the universe contains about 23% of its total mass and energy in the form of dark matter. Stars, the things that we can actually see, account for only 0.5%. They're a tiny, tiny fraction. They're very important because they're the things we can actually look at with telescopes, but the dark matter is the majority of the mass. So I'm going to show you a couple of other examples of why we know dark matter is there. What you're seeing here is a map now of galaxies in the local universe. This map was made by the Sloan Digital Sky Survey. They had a telescope which, again, looked over a large part of the sky, found galaxies, and then just plotted out that distribution in space. And once again, you can see that they're not spread around uniformly. They tend to form into little clusters. And if you look closely, it's kind of reminiscent of that cosmic web of dark matter I showed you earlier, but this is now galaxies. Let me show you another version of this. This is the same thing, a map of galaxies in the nearby universe, except now there are two colors. One of these colors is the real universe, maybe the yellow, maybe the blue. The other one is a simulated universe built on a computer using our understanding of dark matter. Who thinks that the yellow one is the real universe? Is nobody sure? I have one back there. Anybody think the blue is the real universe? One or two. Okay. So that's actually really good because I've confused you. You don't know which is real and which is fake. And that's the point. Our understanding of dark matter is very, very good. And when we perform calculations on it, it looks so like the real universe that you can't actually tell them apart. That means we've done our job well, and we've actually understood a lot about how dark matter behaves. So the pattern of galaxies in space actually confirms that there is dark matter out there. If we didn't have dark matter, our simulated universe wouldn't look like the real universe. And I have one more bit of evidence to show you, in case you're extra skeptical. And that is based on this image. This is an image taken by the Hubble Space Telescope orbiting around our Earth, outside the atmosphere, so it gets nice clear views of the universe. And in this case, it was looking at a cluster of galaxies. This is just a lot of galaxies gathered together at one point in space. And in this image, every single one of those yellow blobs is a galaxy containing billions of stars. But if you look very closely, at the top of the image, there's a very faint arc. It doesn't look like a galaxy, it looks like a stretched out part of a circle. And maybe it's a little too bright for you to see, but on the right, you can see another one of those. So what are they? Well, it turns out they are also galaxies, but they're galaxies that are much, much further away than the big galaxies you see in this image. Unfortunately, I don't have a pointer, so it's going to be difficult, but there is one basically in the middle, right at the top, and one on the right-hand side, just to the right of the largest galaxy over there. So, unfortunately, I can't point them out any more clearly. There you go. One right there, and one near the top. Maybe you can point that one out. Up. Go, just point upwards. Perfect. So it turns out those are distant galaxies behind this galaxy cluster, and their light is being distorted by the gravitational pull of the matter in this galaxy cluster. And this was actually predicted by Einstein in his theory of relativity, where he explained how gravity works. He predicted that gravity itself could deflect light. And so the idea is that we have a galaxy in the distant universe, and the light from it travels towards us, but as it does, it passes by this galaxy cluster, and it's deflected. So instead of traveling in a straight line, it actually gets curved, and that causes the image of that galaxy to be stretched out into this arc shape. And by measuring the positions of those arcs, we can actually figure out how much gravity this cluster must have. And if we can figure out how much gravity it contains, or how much gravity it produces, we can figure out how much mass it contains. So this is another way of weighing the universe. And again, what we find is that the stars in these galaxies just don't contain anywhere near enough mass to explain the presence of these gravitational lensing events. So once again, there must be dark matter out there. So basically, everywhere we look in the universe, we find it's full of dark matter. There's much more dark matter than normal matter. And so we really want to understand what it is. And the problem right now is that we don't know what dark matter is. We can tell that it's there, we can tell that it produces gravity, but we don't know what it's made from. But once again, astronomy is the only way right now we have of trying to get an answer to that question of what is dark matter. And I'll show you one example of how we're trying to do that. So this is a map of our local group of galaxies. This is the region around our Milky Way, the bright spot in the upper left, and the Andromeda Galaxy, the big bright spot in the lower right. And if you look closely, there are a bunch of smaller galaxies, 30 or so of them, that orbit around the Milky Way and the Andromeda Galaxy. And a lot of these galaxies have been found recently, some of them by Carnegie astronomers. And we can compare that to what we think the dark matter around our Milky Way galaxy looks like. This is that same image I showed you earlier. And just to make it clear, the circled region on the left is the same size as the circled region on the right. Now, if you look at the image of dark matter, once again, it contains thousands, tens of thousands of little blobs of dark matter. And in principle, every one of those could have formed a galaxy. But if they did, then that would mean we should expect to find thousands and thousands of little galaxies orbiting around in our local group, and we just don't see them. So what's going on? Well, maybe we used the wrong type of dark matter. These calculations were based on something called cold dark matter, which sounds very unappetizing, but all it really is dark matter that's made from very massive particles. They move around very, very slowly, so we call them cold. So what if we try a different type of dark matter? Well, again, using computer simulations, we can do just that. We can try whatever kind of dark matter we think of and see what happens. So once again, this is a calculation using that same cold dark matter. And once again, you can see it contains a large number of these little blobs, each of which could form a galaxy. There are hundreds and thousands of them in there. But let's warm the dark matter up a little bit, make the particles move around a little bit faster. Well, now things look a little bit different. There's not quite as many of these small blobs of dark matter lurking around anymore. We've actually washed away some of them. I can keep doing this if I make the dark matter warmer still. What we're left with is even fewer of these small blobs of dark matter. We still have a big blob in the middle where the Milky Way would form, but there'd be none of the small galaxies nearby. And so we can actually use the fact that we know how many galaxies there are in a local group to figure out just how warm or cold dark matter should be and start to get some idea about what it might be made from. So I hope I've convinced you that dark matter really is out there in our universe. It's the majority of our universe. And right now, astronomy is the only way that we both know about it and the only way which we have to learn more about what it can be made from. But of course, as theoretical astrophysicists, we'd also like to be able to understand the visible parts of our universe, the galaxies. And so I'm going to hand this back to Juna, who's going to show you some calculations of galaxies in the universe.
So we sit here right under Mount Wilson, and we're going to hear just in a few minutes how Mount Wilson inspires the musicians among us. But Andrew and I are just inspired by the telescopes themselves and what we're learning, as Andrew just discussed. What I'm going to show now is one of the calculations that I've done with my collaborators, where we start with a very smooth universe as predicted by the Big Bang that Andrew showed earlier, that smooth cosmic background. And as time evolves in this movie, you see structure growing. So you see that clumping. Now this is what we're looking at here. These are not dark matter particles. These are actual gas particles, like the regular stuff that you and I are made out of. The small fraction of that traces all of that dark matter actually produces the galaxies and the gas that we see in the universe. And I'm just gonna run this movie back and forth so you can see the diversity of structure as it forms. And the color coding in this movie shows different temperatures. So at the sort of nexus of these filaments, you see sort of hot red blobs, and that's a galaxy forming and supernova going off, so stars exploding at the ends of their lives and heating up gas and creating hot bubbles around it. And this movie will just go back and forth. And at this point, we will hand our microphone over to our colleagues. Stephen, where are you? Thank you.
Thank you, Juna. I'm Stephen McCurry, director of the Pasadena Conservatory of Music, and we are a community music school offering lessons to students of all ages. So if you want to brush up on your music and you're not with us, please check us out. We started last year a series that we call Songs About Place. It's a series that just explores music from different parts of the world or is about very specific places. And to start this second season, we decided to commission a work from our own faculty composer, Matthew Brown. And as we sat down with him and said what the theme of the series was, he decided he wanted to make a piece about Mount Wilson because he had been there recently and had had a moving experience visiting the observatory. And then it was later that I was at a meeting with Erica Clark and was talking about this, and she was coincidentally saying what was going on here at the observatories and their history with observatories, including Mount Wilson, that we realized we had the opportunity to put these two programs together. So I'm really pleased to introduce our faculty composer, Matthew Brown, and his piece about Mount Wilson Observatory. Thank you.
Thank you.